today about chapter 2 of Griffiths. So we're starting here in chapter 2, now that we've completed all of chapter 1 and all the problems. Now we're getting to, probably like the meatiest chapter of this book if you're an undergraduate. This is where you have all your main solutions, your infinite square well, harmonic oscillator. If you're taking, like, say, modern physics, this chapter is pretty much like, your last month to 5 weeks of class is just this chapter 2. As you can see, it's quite lengthy. So we are going to start at the beginning. Now, one of my goals in this video is to really explain it on a level where maybe you don't really need all the formal math, or at least not relying on all the formal math. I don't think I've been really succeeding thus far, so I'm going to try to be a little bit better about that. And one of the places where I definitely did not succeed in the first chapter was I completely overlooked this very important part that we are taking for granted here, which is separation of variables. What does that mean? So, in our case, we are talking about a wave function, and our wave function, capital Psi, is a function of x and t, meaning if I were to plot this capital Psi as a function of x, it would have some shape. For every value of x, there's a unique value of psi. That's what we call a function. We cannot have something that, say, looks like this, because now for a value of x, we would have two different values for psi. So that is not a function. I can have another dimension out there. I could draw, say, a dimension coming out of the page, which is time, and my psi would also be a function of time, meaning that this function would exist in the space coming in or out of the page. I could also just simply collapse it into another dimension because that's easier for me to draw. And basically, if time changes, my wave function changes. If x changes, my wave function changes. One thing that we can do, which will severely limit the number of solutions that we can find, is we can make an assumption here. We're going to use a method called separation of variables. So what that means is that we are considering our wave function to be dependent on position x and time t, and I'm going to say it's like one function that's dependent on x multiplied by another function that's dependent on t. I don't know why he used capital Psi and lowercase psi. Who knows? Sometimes things just become tradition for a reason. It's a little bit confusing, but there you go. That's the way it is. Fortunately, most people are pretty explicit about, say, putting this in boldface and that not boldface or italic script. At any rate, what we have is our total wave function. We are breaking it down into one part that's dependent on space multiplied by another part that's a function of t. This part here could be something like, I'm just going to make up something like, say, x squared. This is only dependent on x. Say it's like multiplied by a constant, whatever. It is only depending on x. Our part that's depending on t could be, like square root of t. Maybe multiplied by a constant. Whatever the function is, it can be literally anything at this point. All that matters is that there are no dependence on x for f of t and no dependence on t for psi of x. They are separable. Now, clearly this is going to limit the solutions that we can have. So we are not able to, say, use something like psi of xt. We couldn't use something like x squared t plus x t squared, because there's no way that I can parse this out to get those separatable. I can't if I factor out an x, I am left with an x inside here. So that sort of solution is out. There are several others. So we are, by making this assumption, limiting the number of solutions that we're considering. However, just because we are limiting the number of solutions doesn't mean that we are not going to get useful solutions. So, as Griffiths says here, the solutions we do obtain turn out to be of great interest. And generally, what we want to do, kind of like how when we were looking at normalization in chapter 1, we found that we could normalize a wave function for any value of t, so we might as well set t equal to 0. Here, what we're saying is that if you apply this method of separation of variables, you can find your solution in a easier fashion, and then after all said and done, then you can patch together the separable solutions to construct a general solution. So this is just a way, this is a tool to attack a problem. Okay, so what does this mean when we do separation of variables? I'm going to go over this because when I've had students in quantum mechanics, and we get to say, like our three-dimensional solutions, or like for hydrogen atom, and then we have to switch over to like polar coordinates, and then we have to do separation of variables. They maybe a bit rusty on it, and it's okay. So there's it's something you just have to kind of practice over and over again and get used to it. Also, if you're not familiar with the math, I think this can be very interesting. So first off here, this is what and I'm going to try very hard to make capital psi look different from lowercase psi. So for our solutions to the derivative of this, so we know that our Schrödinger equation reads like this. And then we have h bar I think it's negative here, or I'm mixing up the negatives and the positives, so sorry about that. You can just imagine one's the complex conjugate. Oh, oops, sorry, that is dx squared. There we go. And then that will be plus h bar over y, and then my potential. So that's our Schrödinger equation. You'll notice that the Schrödinger equation depends on the time derivative of a wave function. So what that means is, what this symbol here means, dt or del t psi, means we want the slope of psi as a function of t. That's what we want. That's what this means. So if psi and t, let's say it's a straight line, then del psi del t would just be the slope of that line. It would just be a number. Our slope would be that guy. Now our wave function is going to be a different shape, but it's still going to be the slope of that shape. Del squared del x squared, this means the slope of the slope. So if I had my straight line again, I would take the slope of that, I would get a constant, and then the slope of my constant would be 0. So slope of the slope. This terminology, derivative, just means slope. In the case of a straight line, it's a constant. In the case of everything else, it is also going to be a different function. Since these are separable, when I take the slope of this guy, this is just a constant with respect to t. So this guy does not change with respect to t. But this guy does. Same thing happens when I take the second derivative with respect to x. This f of t is not dependent on x. It just flat out doesn't change. But this guy does. And then I'm using full derivatives. So I use this when I have a partial derivative. That's when something's a function of more than one thing. I use the d's when it's a full derivative. And that's what we have here in this line of Griffiths. Just the same thing. He just didn't write out function of x or function of t. So then if we replace that into our Schrödinger equation, which was del psi, capital Psi del t, negative h bar I over 2m del x squared, and then, oh yeah, I guess, there we go, h bar over I, v, and then psi squared, if we just flat out replace those through. So we are just going to take that guy, we're going to replace it with lowercase psi ddf, or df dt, and then we have minus h bar I 2m, and then we get our I want regular derivative, and then f, and then plus h bar over I, and then we have v, and then we had, instead of capital psi, I'm going to write lowercase psi f. Then all he did here was multiply through by this, Hold on, I messed up my wave function. I always forget which way it goes. I know I should just work it out from the units. Yeah, it's h bar over I. Oops. Okay. I was gonna say I got one of them upside down. Okay, let's go ahead and fix that. That's what you get for going off of memory. Don't ever go off of memory. Your memory is not good. Actually, let's just erase all of that. Okay. And then I'll erase that one. There we go. Okay, so that was positive, that was negative, and that'll be h bar I v psi. Now, our wave function, so we're going to, I'll just write it out again here. That's h bar I over 2m del psi squared del x squared. And let's see, that's going to be minus I over h bar. Probably still messed up the sign there. Times psi. Okay, then we just straight up replace that. This is going to just be our, so d psi dt is going to be psi lowercase df dt, and then we have h bar I over 2m, and now we have full derivative with respect to x, and then we're going to have that f out there. It's just a constant with respect to x minus I h bar, and then we have v, and then we have lowercase psi times f. Now what he did here was he just multiplied through by h bar divided by I. So I could rewrite this as this guy. I could say plus 1 over h bar over I. And then if I multiply everything by h bar times I, so whatever I do to one side, I have to do to everything on each side of the equation. So I gotta multiply everything by h bar times I. That gives me h bar squared times I squared, which is negative h bar squared over 2m d. I'm very attached to that partial derivative apparently. And then we have v lowercase psi f. So there we are. We are back where Griffiths is now. He just took a couple, I mean, not really that bad, but he just took an extra, like, skipped a step there. Okay, here's the part where most people forget about separation of variables, and that is then you have to divide through by your function. So now you have to divide everything by psi f. The reason we do that, so at the end of that I divide everything by psi f, my voltage is left alone, or not voltage, it's funny, they have he has a footnote here saying it's tiresome to say potential energy function, so most people just call V the potential, even though it invites the occasional confusion with electric potential. And then I did that. Sorry, V is just the potential energy. not necessarily a voltage. A voltage would be potential energy divided by a coulomb, a charge. Okay, so that cancels, and then that cancels. What did that accomplish? It gave us this. So now what I have is f is a function of t, and it's together with its derivative, which is also a function of t. So over here, we have things that depend on t. Over here, we have things that depend on x. And we can keep the v here, because we are talking about energy. But this is our goal whenever we are doing a separation of variable, like our purpose for doing separation of variable is to have things that depend on one variable on one side of the equal sign, and things that depend on the other variable to be on the other side of the equal sign. So separation of variables is like, you know, the whole idea is to separate the variables. We want the variables to be one on one side of the equation, the other on the other side of the equation. I don't know why, but it just seems very common that this step is the one that is forgotten after, you know, you took your partial differential equations class. And then like a year later, you're in your quantum mechanics class, and all of a sudden you have to like apply this stuff that you only learned in a math class to physics. And I think it's because that step gets sort of glossed over in math, whereas for physics it's like the most important step. And that's because we want things that depend on one physical constant over here, things that depend on the other physical constant over here, equal but separate. Doesn't work for people, but it works really well for physical constants. So what this means is that if this guy, it depends on a variation with time, this guy depends on a variation of x. And if this is true for all t and all x, that means that this must equal a constant, and this must equal the same constant. If this is true for t equals 0, and is true for t equals a billion, it has to be true for all t in between 0 and a billion. I can't have this equal, say, 5 when t is equal to 0, and then equal 7 when t is equal to 15,000. It has to always equal the same thing, because this guy doesn't depend on t at all. That's why we limited our solutions. So our solutions are severely limited at this point. That means that both of these have to equal a constant. It's the only way that this can be mathematically true. And I wish I could draw better to explain it. Maybe I'll think of a way to make a good illustration to draw that. But I hope I made the argument of why they have to equal a constant. This has to be the same number for any value of t. This has to be the same number for any value of x. So he makes a good argument for why he uses the letter E here. I like to always make the argument from units, and that's because, so one of my goals of this video is to really demystify quantum mechanics, even for people who are not physics students. And that's because it is just so misused in popular culture. One of the things that is so misused in popular culture is energy. So let's look at the units of this. H bar, that's a physical constant. Like, it's Planck's constant. It was found in the early 1900s. It's been refined over many experiments. It's a way for measuring energy times time. That's what Planck's constant is. This is the smallest quanta of energy change possible with a second. This would be like your pixel of energy. We don't have energy packets that have, say, a value of 1/2 h bar. This is the smallest amount of energy difference we can ever have times a second. So this is joules times seconds. df dt, this function depends on time. It is the slope with respect to time. If you're driving a car going 50 miles per hour, that is a slope with respect to time. You go 50 miles every hour, per hour. The units of that, you're going to have over seconds per time. It doesn't matter if it's velocity, 50 miles per hour, or if it's I can make 20 YouTube videos per day, that is still a rate. That has a unit of per time. That means there's a fraction and the time is in the bottom of that fraction. I have joules times seconds multiplied by something that has 1/seconds. Those seconds cancel out. I am left with joules. Joules are energy. All energy is joules. If somebody says that they can feel your energy, that means they can feel your joules. There is no energy that's not a joule. That's what energy is. So that means that this constant that this has to equal has to be an energy. Now here we're just rearranging it. So here, dividing both sides by I over h bar. So I have this guy, looks like this. It equals E. I divide both sides by I h bar. And then I get this. Because it is more aesthetically pleasing to us, if you've done a lot of differential equations, also there's a condition that we have in our Schrödinger equation that our solutions have to converge. They can't blow up to infinity as we go to infinity. That's why we want this negative sign in here. These are absolutely equivalent expressions. It's just more aesthetically pleasing to have the negative sign there. Oh, whoops. And then they multiplied both sides by f. I skipped that step. Those canceled out. And then I need to erase that guy there. And I'm clearly erasing too much. There we go. df dt, and then we have df dt. Now if you're familiar with partial or differential equations, or you haven't taken that yet, or you never plan on taking it, this means that the slope of my function equals my function times this constant. The solution to that, the function that is equal to its own slope, is an exponential. So the solution to this guy is we have some constant, I'll just call it c, e exponential to the negative e h bar t. You could also just like multiply it's like one of the most pleasing things about Leibniz notation is that you can do this, or you could do df equals integral dt, and you could just like straight up integrate that. But then you just have the same thing. Oh, the function is equal to its own integral. And that means that it's going to be e to the x, or in this case e to the t, and it's going to have this constant value out in front of it. My husband would talk about a guy that he went to, like he was in undergrad classes with in math, and he said the guy was so dumb he couldn't integrate e to the x, which is really funny if you've ever integrated e to the x. Probably not so funny if you haven't. Okay, now we do the same thing for our right-hand side of the equation, where we had this expression which was with respect to x, and then all you did here was multiply everything by psi, just to get it out of that denominator, and it's more pleasing that way. So this, the solution to this guy was trivial. It's just an exponential. This guy, the solutions are not trivial. They depend on what your potential looks like. This is the time independent Schrödinger, independent. This is typically what you're going to be solving for. So if we have something like a solid, with a bunch of atoms in our solid, and they're making like some well, or depending on how our solid is configured, whether it's a metal or that has a particular potential, like a Coulomb potential, or if we have a piece of carbon that has a different potential, or we have a ideal gas that has a van der Waals potential, those all call for different solutions to this equation. So it very much depends on our potential energy. So in the case of condensed matter physics or chemistry, you're looking at, those chemical bonds in your solid. That's going to depend, that's going to dictate what solutions to your Schrödinger equation you can have. Now this turned, since we did separation of variables, this turned our partial differential equation into two ordinary differential equations. And now they're both much easier to solve. This is just our result for our time-dependent function. It does not depend on the potential. Now, the rest of the chapter, as he says, is all about solving for different potentials. So just looking at some simple cases, different potential energies, and using the time-independent Schrödinger. But I do want to briefly talk about why it was okay to limit our solutions to separable solutions. And he lays out some really good arguments here. First of all, the time-independent wave function, just the lowercase psi x, that guy, is not the wave function. Your full wave function does depend on time. It must depend on time. But so then why go through this step to make sure they're separable? Well, the first case that he brings up is that they are stationary states. So even though clearly our wave function must depend on time, if we look at the probability density function, our probability density function looks like this. If I integrate that over all space, I must have a 100% chance of finding my particle somewhere. If I integrate this guy, you see that our time factors are just going to cancel out. I get e to the plus I e over h bar. I think I said e too many times there. And then times this. And then we just add those together. So we have e to the plus I e over h bar minus e over h bar t, and those just cancel out, and I get that just equals 1. So my time cancels out completely from my probability density function. And I also did a video way back when in chapter 1 where we showed that for any solution, the complex conjugate is not times the wave function itself is not going to depend on the time. So our probability density is independent of time. Also, our expectation values are independent of time. So if we want to find the expectation value of the position, it's going to correspond to, say, a stationary state. Now you will notice, and you probably notice in the other answers, that if we, say, did the expectation value of momentum, on the other hand, nothing happens. It gets 0. And that's because, as he says here, nothing happens in the stationary state. That does tell you a lot about it. It can tell us the probability of the particle, and that's very useful. And it's helpful to solve the stationary state, because once we solve for the stationary state, then we can expand to a dynamic state. So it is very helpful to look at things in the stationary state, even though we know it's not a complete solution. Okay, now we have that these are states of definite total energy. And this is where he argues of why he should have used E, which is a good argument. I just think that you could go even simpler than that, just looking at the units. Okay, there's a word that if you are taking any sort of condensed matter physics, you are going to get used to, and it's called Hamiltonian. Hamiltonian is kinetic energy plus potential energy. Kinetic, I probably misspelled that. Kinetic energy plus potential energy. So basically describing the energy of our system. In classical mechanics, kinetic energy, Ke, equals 1/2 mv squared. I multiply top and bottom by m, which is effectively multiplying by 1. And what I get is m squared v squared over 2m, or I get momentum squared over 2m. Plus whatever our potential energy is, that's going to depend on our solid or our system. As we found in chapter 1, we want to start thinking of our momentum not as mass times velocity, but rather we think of it as h bar over I del x. So if I take h bar over I and then the derivative with respect to x, that's when I get my momentum. So I can write my Hamiltonian as an operator by replacing the p, replacing this with my operator value. So then I get h bar squared over I squared, which is -1, that's hence the negative sign, over 2m, And then I have del squared del x squared plus my potential, which is a function of x, we're going to say. So then if we throw that into our Schrödinger equation, what we had for our time-independent Schrödinger equation was this. So our time-independent Schrödinger equation is this guy. Oops. Total derivative. Doesn't really matter, but. And then remember we multiplied through by psi. So then we had V, I wrote it backwards, V psi equals E. So now my Hamiltonian, I could say, is acting on psi. So I get this guy, dx squared plus V acting on psi, E psi. Or I get my Hamiltonian operator acting on psi equals energy psi. This is probably the most common way you're going to see the time. Like if you looked up on Google, this is the most common way you will see time-independent Schrödinger equation written, because it's nice, it's pretty. The expectation value of that total energy is just going to equal the energy. So if I do psi complex conjugate times here, I would write all that out. So I have negative h bar over 2m d dx squared psi plus this guy times psi. Oh, whoops, I already put in my psi. Too many psi's. There we go. But as I just said, all that junk equals E psi. So there we go. Now I have my integral. I have my expectation value of my Hamiltonian over dx equals this guy. And I could just pull my energy outside my integral. And I know that that equals 1, because that's the probability of finding my particle anywhere. So my expectation value for my Hamiltonian is just the energy. Do the same thing for the Hamiltonian squared. We end up with we go through the exact same argument. It's just that I end up with E squared at the end of it. So I get E squared. Then if I want to take my standard deviation, I take this result, which was E squared, minus the first result, which was E, but I square it, and we get a big fat 0. So that means there's no deviation in our expectation value for our Hamiltonian, i.e. every time we measure the Hamiltonian, we're going to get the same Hamiltonian. We're going to get the same energy. So the conclusion here is that the separable solution has the property that every measurement of total energy, that's what Hamiltonian is, total energy, returns the same value for energy. And that's why he chose E for that. I personally always like looking at the units, because I think it's very important to always remember that even though we're doing some really complicated math, this energy from a quantum system is no different than any other energy. Just because it's quantum doesn't mean it's special, and it most certainly does not mean it's not measurable. With this result, with this, like, maybe it looks super smart mathy result, whatever. What this is saying is that if I measure the freaking energy I'm always going to get the same energy. If I make a measurement to measure the total energy of my system, I get back a value in joules. This is physical, read by an instrument. So just because energy is quantum in origin does not mean it's not measurable. In fact, the fact that we have the expectation value, that it means that it is measurable. It is an observable. It might be physically difficult to measure a quantum system because they're little, but it is not impossible to measure it. Okay, now the last part is that this is the mathy bit. The general solution is a linear combination of separable solutions. So what that means, for any number of solutions that we found by doing the separation of variable, we can just make a linear combination of them. That literally means we just add them all up. So if I have psi 1 corresponding to energy state 1, I have psi 2 corresponding to energy state 2, I can simply take a summation of them all. So I can just literally find, my psi, capital Psi, that's a function of x and t. These are going to have, say, some constant out in front of them, c1, and then we have psi 1 x e to the I e1 h bar t plus c2 psi 2, that's a function of x, and then e to the negative I e2 h bar t, and so forth. So, for example, if this equaled a 2 and this equaled a 3, I would just get a summation of them all. And my total wave function would be 2 plus 3, 5. That's what a linear combination means. We just add them together, which is very nice because we do have separate energy states, hence the term quantum mechanics. There are separate energy levels. All of those combine into our total wave function, and it is a linear combination of all the solutions, which is really nice. That's one of the advantages to these separable solutions. If our solutions were separable, then this is a consequence of that. Again, it is for a very, very, very limited number of solutions to our original partial differential equation. But one of the advantages to all the solutions that we do get when we make that limitation is that we can also make this linear combination. So the main point is that once you've solved the time-independent Schrödinger equation, you're basically done. Once you've solved the time-independent in space, or, Hamiltonian of the psi function equals E, once we've solved that, and we know that the solution to the time part is basically trivial, it's going to be this guy, then we just take a linear combination of all the solutions. And that makes it a very, very powerful technique. That went a little bit long, but hopefully that was helpful in giving you some justification for the rest of the chapter, which is basically just looking at time independent. And that's it for today.